Start recording. I have to mute off. Feedback is too much. So here we've got some equations, and we're going to use the switch to the exponential or switch to the logarithmic method when we solve these. Today we'll start with the logarithmic properties after we go over the homework. All right, well, I wrote the first three on the board here. So with this one, we can just switch it to the exponential, right? So when the log equals the exponent, and the value is x, so 5 to the third power is the value. Now again, if you can interpret the log expression, you can do it that way too. All right, and the same thing here, we can rearrange this to the exponential. So we got the log equals to 3, so that's the exponent. This 1/8 is the value, and this time we don't know our base. So the base with an exponent of 3 equals 1/8. Okay, well, now again, there's ways of solving this that we're going to have available today. Maybe you already know. We can log both sides. But in this case, let's go ahead and see if we can find some integer that uses an exponent of 3 to get 1/8, right? And that would have to be 2 to the third power. So this is 1 over 2 to the third power, so then that's x. X equals 1/2. And again, we can do the same thing here. So if we rearrange this logarithmic expression, we have our base, we have our value, and in this case, the exponent is a variable, right? So 5 to the variable exponent equals 625. Okay, so we can do the same thing here. Now, again, we're going to have other options. Maybe you know how to log both sides, but let's first, can we represent 625 using base 5? And the answer is yes, because this is 5 to the fourth power. So x is 4. Okay, so notice basically all of these have the variable in a different location. Here the variable was the value, here the variable was the base, here the variable was the exponent, what the log equaled. Okay? Everybody all right with that? All right, so we're going to go to the next three. The next three were a little more involved. 2 of the next 3 were exponential. Okay, so we got the 100. All right, so e to the negative 2x equals 1/3. Okay, so now we're going to switch this to the log. Again, we have the exponent. The base is understood to be e, and this is the value. Okay, so since it's the base, we're going to use ln, since it's base e, and the ln is going to equal our exponent, so the ln of the value equals negative 2x. Okay, and then you just either divide by negative 2 or multiply negative 1/2. And then that's just buttons on a calculator, and you can just do that. All right, and then the next one, 104, this was a more involved log expression. Okay, so it's a little more involved, but it's the same kind of idea. Whatever the log equals is the exponent, the value, and then here's our base. Okay, so 5 squared equals this trinomial. Right, that's 25, so if you subtract, now this is not factorable, so you're going to have to do the negative b plus or minus over 2a. because it's not factorable. I know you guys know how to do that. Okay, so we've got one more. Any issues on that so far? Okay. Let me double check. Take a sip of tea. We'll finish up. All righty. So now the last problem, and that was the one of all of these that was a bit involved. All right. So we want to solve this problem. Now you can't multiply the 8 to the 10. That's mistakes people make. You react to what you see 8 first, you see the multiplication, you want to make that 80. But you can't do that because 10 has an exponent. So you got to apply that exponent first, and we don't even know what x is right now. All right, so we want to get this so that you have your base and your exponent by itself. So dividing by 8 is the first step. Okay, now we can switch this to the logarithmic. The base is 10. That's our exponent, and that's our value. Okay, so the log of the value is going to equal the exponent. Okay, and in this case, you don't have to write the little 10 by the g. If base is 10, people just understand that's the case. It happens so frequently, people don't put a little 10 there. Okay, so then just add 7, multiply a half, and I know you guys can do it. Okay, y'all doing all right? Okay, so we'll look at the homework. We'll take a couple sips of tea. My mom bought me some 10 Ren tea like 18 years ago. I still got about half of it. It's like this huge container. You only need like a couple little nugs. Trick, just a couple little nugs. I wonder if I'll be able to finish it before I pass. All right, so here we got is the homework. So which one's on the homework you want me to go over? Do a summary like I always do, and I'll point out the two things that I made mistakes on. One of minor, actually both are kind of minor. So notice how I broke this down, right? Now I'm able to go just by using my head from the function to the inverse. Maybe you can do that, maybe not, but so I didn't really show steps when I went from the function to the inverse, and then I labeled down what the transformations are to the parent function, and then I put the domain and range like we've been doing in class. Now the instructions for the homework, they didn't really ask you to find the domain of the inverse or the range of the inverse. But that's what I did, because again, I want to be thorough. All right, so here there's no massive transformation, so you can just take the place where it normally would be and then move it accordingly. All right, so notice right here on the logarithmic function, when this equals 0, right, that's not, that would have to be -3. Right, so when the y is 0, -3. Okay, and when x is 0, that's the y-intercept, you get ln 4. All right, and notice if we have the horizontal shift to left 4, that means the vertical asymptote goes over here, -4. And so one way to do this is just to take and switch the coordinates. So vertical asymptote, horizontal asymptote, y equals -4. The x-intercept -3, y-intercept -3. The y-intercept ln 4, x-intercept ln 4. So it's just another way of thinking about it. All right, let me just point out a few things. Now here's one, number 75. This one had a domain dilation because it was 2x. So instead of crossing at 1, it would have shifted down to 1/2. I put the 1/2 there, but for some reason I put the graph over here for the black. It should be over here. I did it correctly when I did the inverse, right? So notice the 1/2 range dilation. So instead of crossing at 1, it's going to cross at 1/2. And again, the only way the asymptotes change is if you have a vertical or horizontal translation. So with ln, you need a horizontal translation. You need to go left and right. And with exponential, you need a vertical translation. You need to go up and down, right? Okay. So let me see. And then here I went ahead and like I showed you all in class, I added, since this was just horizontal and vertical translations, to what would have been 0, 1 and what would have been 1, 0. I just added the horizontal and vertical translations, moved that new point, and so the vertical asymptote moved over 4, the horizontal asymptote moved up 5, or my bad, 4. Okay, and then notice this kind of switches. The horizontal translation plus 4 becomes vertical translations plus 4 when you switch to the exponential. Because again, these are inverses. Now the second one, 80, this was another mistake I made. So here we flipped over the x-axis for the exponential, and so it should have been growing as you go to the right. And so this right here, I flipped it the wrong way. It should be going down on the right. Sorry about that. It should be going down on the right, approaching the horizontal asymptote to the left. So this pink is flipped left and right wrong. All right. Okay, and so then, blah, 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 well, you aren't asking me for anything. So now here, down here, I went ahead and added a green line to indicate how the effect of the range and domain dilation is. Okay, so notice range dilation, you're going to go much higher than the normal graph. Domain dilation, you're going to stretch farther away than the normal graph. So you want to do that before you do the translations. So before you start moving when you're on the axis. So domain dilation, right? Okay, so what else was there? Yeah. All right, well, I guess you're all good. Well, let's look at some properties of logarithms. I'm going to show you where they come from. All right, so let's say we wanted to represent the number 30. Okay, well, if we're using base 2, we're going to need the logarithm to represent 30. We're going to need the correct exponent. So we would use the log base 2 of 30. That would be our exponent. Well, what if we wanted to use base 5? Okay, that would be okay. Now we're going to need a different exponent. It's going to be based on 5. So that's what we'll have. Okay, notice whatever logarithm you is going to give you the exponent to the base that would be necessary to equal the value. All right, we could do this with base 10. In this case, we don't need to write the little 10 by the g. That would be understood because we're using base 10. And if we use base d, to get a value of 30, we need the correct exponent to base e. So we can represent 30 in all these different ways, depending on what our purpose is. Just to put the logarithm in the exponent that would get the value and apply that to the appropriate base. Okay, so if we're multiplying, if we wanted to change this to base 10, we would just use base 10 twice and apply the correct exponent. Now what happens when you multiply common bases? You add the exponents. All right? Now what if you're dividing? Well, if you're dividing, you can do the same thing. You can convert these to whatever base you want. So let's just convert them to base 2. All right, now what happens when you divide at common bases? You subtract the exponents. Right? So if you log multiplication, what you're doing when you do that is you're skipping this step. This is going to find the exponents that you're going to need to use base 10. The log of the multiplication equals the sum of the log of the products. Same thing here. If you were logging that, I mean, this is just going to skip this step. Well, actually, log base 2. This is just going to skip this step. This is really what you're doing. If we want to change this to base 2, what exponents would we use? So we tend to skip this step. All right. So then that means we would subtract the exponents. So if you log a quotient, it's the log of the numerator minus the log of the denominator. Okay, and so likewise, what if we had some value with an exponent? Well, we can change the value that has an exponent, right? So let's say we wanted to use base e. Okay, then notice what happens. Now you have a power outside parentheses, so the power multiplies to the log. Right? And what does that mean? Well, that means if you want to change this problem using base e, and you ln that, you multiply the exponent to the log. Okay, now again, when you do this, you're skipping this step. When you log something, you're changing it to a certain base so that you can use the property of exponents. Right? That's where this comes from. And it's usually this middle step that gets skipped. But that's where that is. All right, now again, I'll show you the summary of these properties in a moment. All right, the last thing is very helpful, and it's called the change in base property. All right, so I'm going to show you where this comes from. So let's say we had this problem, and or what if we didn't want to use this base? What if we wanted to change this to base 10? Since we don't have buttons on our calculator, right? If we wanted to take a log using a different base, we can't just, there's no button on our calculator. So if we wanted to use base 3, we can't push a button on our calculator that gives us that base. So if we wanted to find this, we wouldn't be able to do it. All right, so let's see how to handle that. So I'm just using variables to represent quantities. All right, so let's rearrange this. Well, this is the exponent. We know that's our base, and we know that's our value. Hence, the letters I chose. All right, so the base has the exponent, and that's going to equal to the value. All right. All right, now let's go ahead and log both sides. LOG. You can use ln if you want, because it doesn't matter how you change the base. The properties of exponents don't change. So I'm going to LOG both sides. Okay, now we got the property of exponents, the property of logs that we just had. Oh my God, I should have done that. And that's because that's a power. So this becomes y log b equals log b. And now we have a way to find this y because notice you're just dividing. Right? So if we wanted to find what I mentioned earlier, that, just take the log of the value divided by the log of the base. So we're converting this to base 10, essentially, is what we're doing, because those are the buttons on our calculator. And again, what we do, we rearrange this to the exponential, and then we log both sides. We use the property of logarithms when you have an exponent as part of the value. And then now we can divide. This is called the change in base property. And that's where it comes from. Okay, and so that would be, what did I want to list that? Yeah, that would be these properties. Now, one of the reasons these came up is because people started recognizing that you could use properties of exponents to make calculations easier. So people had a huge book that were developed by a lot of different people starting in the mid-1500s. This guy Napier, N-A-P-I-E-R, came along and began that process of figuring out how you could represent numbers using exponents to base 10. And so they came up with a whole big book where they would tell you what those numbers would be. And so here, you would log this, right? You would get the number that this would equal by looking up what A times B is. And then you would be able to find out what these two numbers are. So you would look all these up in a book. So if you knew what A was, you could look up the log of A in the book. If you knew what B was, you could look up the log of B for the book. Then you could add these two. Then you know that number, and then you can reverse engineer it. So if you have two numbers that are extremely difficult to multiply or divide, and that's where this all began. And it took on a life on its own in other ways. Okay, so today what we're going to look at is how to apply these properties. There's a couple different ways. We're not going to start solving equations just yet. That's going to begin next week. And then we're going to finish up with modeling data, modeling exponential and logarithmic situations, which is currently going on right now with COVID-19. Okay, well, first of all, and some of this that I'm pointing out is really going to be helpful for calculus, because when you start doing derivatives and integrals of this thing, a lot of these properties come in handy. All right, so let's say we had something like e to the log of the square root of e base of 20. Now, what the heck is that? If this was just e, not square root of e, then this would just be 20. Because this would be the exponent to represent 20 using base e. So that would be no problem. But it's the square root of e. So you can't just do that shit. So this can't be 20 because the root e base for the logarithm isn't the same as the base we're applying the logarithm to. All right, so this is tricky. So let's rearrange this and see if we can figure this out. All right, so we're going to rearrange this. We got our base. There's our exponent. And this is the value. Okay? So the log of the value, the log of y. Okay, now we're going to use log base e, and it's going to equal this exponent. So the log using base e of y is going to equal this exponent. Now I'm purposely not putting ln. That's what this really is. This is really ln. And I'm purposely not doing that. But if you wanted to put this as ln, okay. But I'm purposely doing that. That way you can kind of see that if these were the same base, then y would equal 20. All right, well now what do? Let's use the change in base property. Okay, So we're going to do the same thing, the log of 20 over the log of base e. Okay, well, this is really the 1/2 power of e. Right? Oh, well, now look, we got the power as part of the value, so we can pull the 1/2 out and multiply it to the log. All right, we're almost there. Now notice, now we don't have to worry about the square root of e. And this 1/2 is in the denominator. And so if you put a 1 there times log, this is really the reciprocal of 1/2, which is 2. So this is going to become 2 times log 20 over log e. And now we can reverse the change in base property. Oh, so now we have this equal to that. Now we can reverse the power property. So if the 2 multiplied the log, that means it originally was the exponent of 20. All right, now we have 2 logs that have exactly the same base. So the values have to be the same. And so y is 20 squared. I know, kind of kooky, but okay. Well, let's look at another one that uses the same thing and does that with 2. All right, so let's say we had, what was I doing? Okay, so same kind of idea. Now, again, the base that we're using for the logarithm isn't the same as the base we're applying the logarithm to. So if this was 2, that would just equal 50. It's not 2. Okay, so we'll do the same thing. We'll rearrange this to the logarithm. So the base is 2 here. That's our exponent. And this is the value. Okay, so the log of the value is going to equal our exponent. The log is going to be based on 2. Okay, now when we did the last problem, we had this is e and that is square root of e. So we just needed to get rid of the square root of e in order to get the bases to be the same. 2 and 3 do not have any common factors. So what we're going to have to do is the change in base property twice. This becomes the log of y over log 2. And this becomes the log of 50 over log 3. And now, when we go ahead and solve for the log of y, we're going to multiply log 2. Right? Now, if we want to find y, we couldn't do the same trick that we did earlier, right? Because 2 and 3 aren't multiples of each other. Not only that, which one do we choose to reverse the change in base property? Because we could do the log base 3 over 50 times this. Okay, well, so now the best way to handle this now, because of what we have, is to go ahead and reverse back to the exponential. right? So we want this value. That's the exponent. And since I went ahead and changed everything to be base 10, that's what happened when we did the change of base property. Now everything is base 10. So our base is going to equal 10. Okay, so then y equals 10 to this. And now you can at least do it. You wouldn't have been able to put this in your calculator any other way, unless you wanted to do the change in base property right here. Right? And then you could use your calculator. That would become the exponent, and then just apply that to 2. Okay, so fancy ways of seeing how to rearrange this and organize this. These things can become interesting. Okay, so we got 2 more examples we'll look at. All right, so let's say we had, and I'll just use ln. Okay, now we won't worry about domain issues. We're just going to go ahead and what's called expand this. So right now, everything has been contracted into one logarithm. And so what we want to do is we want to reverse the properties and then expand this. Have this as a sum or subtraction of logarithms. All right, well, external to the expression within the brackets is our exponent, so that now can multiply to the ln. Okay, well now we got division. So now we can do the ln of the numerator minus the ln of the denominator. This 5/2 is still there. Notice I'm multiplying both by 5/2. Okay, now this expression we can't do anything about because there is no log property when you're summing values. Because when you sum common bases, you can't add the exponents. You got to multiply common bases. So that's not a multiplication to get that value. So this is going to be unsimplified. But we can do something here because of the 3. So the power is part of the value. So 3 times the 5/2. Now there's a reason why this is important. When you're modeling exponential data, it's very tricky because little subtle changes can have an astronomical effect. So if you go from 2 to the second to 2 to the third, that's 100 to 1,000, right? So a small change in 2 to 3 exponent goes from 100 to 1,000. So when we do this, what we're doing is we're linearizing this. Notice there's no more exponents except in this expression. And I'll show y'all when we get to next week or maybe the week after how people do that, what people do when they model data using logarithms. This is part of it. Okay, so this is called expanding. We went from a single logarithm, and now we have a sum or difference of logarithms. Okay, now the next thing would be called contracting. And that's when you want to shrink down into a single logarithm. All right, so now I'll use log. So let's say we have log. Now, this would be true for any logarithm. So we could have base 3 here. We could have base 30 there. We could use ln. It wouldn't change because the properties of exponents when you have common bases is true for all bases. All right, well, when do you subtract exponents? when you divide. So this expression divided by that expression, which means I'm going to multiply the reciprocal to represent dividing by an expression. Okay? All right, well, now we might be able to do something here because maybe we can simplify. And that is true. We got some, I did this on purpose. So factors of 4 that add to be -5, 5 and -1. Okay, and here factors of 2 that add to be 3, 1 and 2. Okay, and then notice what happens is we have common factors in the numerator and denominator. And so we can divide those off. So we divide the wrong one, the x plus 1. We divide those. All right, so what do we have left? X plus 2 over.
This is the worst thing. I'm fucking serious right now.
Much simpler. Now, if we wanted to now expand that again, notice if we expanded this, it's much simpler than what we started with. So if we, for whatever reason we wanted to do this, it's now much simpler. Now, the reason we contract, we usually do this when we want to solve an equation, right? So if this equal to something, contracting it to one logarithm, say this equaled 8. Now we can reverse this to the exponential. We couldn't do that here. All right, say we're modeling something and we want to linearize it. That's kind of complicated. So contracting, simplifying, and then expanding in, now our linearization model is a lot more manageable. So that's kind of why we do this. Okay. Y'all hanging in there? Anybody want to ask me anything? Okay, that's all I got for y'all today. So y'all take it easy. I'm gonna go ahead and get out of here.